All right, so I'm continuing with our flow sheet. Problem one, we had a stoichiometric reactor. Remember, stoichiometric reactor, we could consider a single reaction. We had to specify the chemistry, so the stoichiometry of a reaction and a conversion. Okay, and we could specify if we wanted our reaction to take place isothermally or adiabatically. Then we had an equilibrium reactor. So in our case, we had a single reaction. Okay, the difference between equilibrium and stoichiometric is it could model the case of multiple reactions, series or parallel, you can specify. Um, and then the other difference is if you have thermodynamic data to compute the equilibrium constant, you could specify conversion with respect to equilibrium. And then along with specifying conversion with equilibrium, you could also specify the approach temperature, right? And the idea is that my equilibrium constant's a function of temperature. So specifying temperature goes one in hand with specifying conversion. Um, Now in this case, we're going to model, we're going to look at a Gibbs reactor. Okay, and so I still have the same flow sheet open. I'm going to delete my equilibrium reactor, and I'm going to swap in a Gibbs reactor. Right, in all cases, stoichiometric, equilibrium, Gibbs, they all look the same. Okay, so I have my same reactant stream, so pure DTBE, 100 kilomoles per hour, 110 degrees C, and 760 millimeters of mercury. Okay, and just as we keep playing, right? If I were to delete pressure and I wanted to figure out at what, oh, actually, no, I want to specify a temperature of 760. Let me specify a pressure of 760 millimeters of mercury. But if I want to find the boiling point temperature, right? We're coming at 110 degrees C. It's just below the boiling point, which is 110.894. Okay, so I'm going to delete that. I'm going to change this back to 110. Okay, so it's just below the boiling point. Okay. Now, Gibbs reactor. So what's key for a Gibbs reactor is I need to have all of my reactants and products listed here in my component list. I don't need to specify the chemistry. Okay, I'm not specifying the chemistry. CHEMCAD is going to take my inlet stream to my reactor, okay, and it's going to break those molecules up into atoms, right? So you can, calculate that resulting change in Gibbs free energy from the corresponding Gibbs free energy formation, right? So I'm going to take that molecule, I'm going to break it up into its individual atoms, okay, and then for the product stream is based on these atoms. Okay, I'm going to calculate or figure out the distribution of components, DTBE, acetone, and ethane. I'm going to figure out the corresponding distribution of those molecules to minimize the Gibbs free energy of my system. Okay. And so how is it going to determine the Gibbs free energy that minimizes my system? Is, well, I have Gibbs free energy of formation data to form, right, all of those components, right, and the distribution, right, is going to have to conform to a corresponding atom balance. And so it'll determine the corresponding distribution of my components in my system to minimize the Gibbs free energy of my system based on the internal formation data. Okay. Pretty cool. So I'm not going to specify chemistry or anything whatsoever. Okay. Key though is any possible products have to be listed in my component list. Okay, so we're going to have this constraint that when it tries to minimize my Gibbs free energy, it's going to be dependent on the components listed in my component list, right? It's only going to have, or only going to use formation data, right? Or only try and include those in our calculation. All right, so in terms of my Gibbs reactor, okay, again, I'm specifying if it's adiabatic, isothermal, or I can specify heat duty. Okay, I'm going to go back to this, first case of assuming it's isothermal at 154.6 degrees C. Okay, great. Okay, reaction. Okay, I'm going to use vapor or mixed phase. Okay, you could also specify liquid. You could specify liquid phase only if it's a liquid phase reaction, but in our case, it's going to be vapor phase reaction. Okay, and where it's vapor or mixed would be if I have two-phase equilibrium. You could again specify, so if we are reactants coming in at 760 millimeters of mercury, you could specify different pressure for the reactor. You could specify pressure drop, right? All of that good stuff. Okay, but I'm just going to specify it's isothermal. Okay, and then we'll calculate a heat of reaction. Okay, So if I had a liquid phase reaction, I could try and account for non-idealities. Okay. But that's all, right? This is all I need to specify, right? These others, okay, would be I could define components that are solids, okay, or I could specify components what are inerts. So even if they're my component list, I can eliminate them from that calculation where I'm trying to minimize my Gibbs free energy. Okay, but all I'm gonna specify is the temperature. Okay, okay, cool. So then it's just showing us the composition, right? The atomic composition of those molecules in our system. Okay, great. And then I'm gonna run it. Okay, so I'm gonna run it. I double click, right? It's going to show me the corresponding heat duty. Okay, so there's my heat duty. There's the heat of reaction that it calculates for this process. Now, the heat of reaction, they actually give us an extensive heat of reaction. So if I'm comparing this to my equilibrium or stoichiometric, it's going to be slightly different because there, for the heat of reaction, it would give us an internal value or intensive value in kilojoules per kilomole. Okay, here it's extensive in terms of megajoules per hour. Then we get a heat duty, also megajoules per hour. Okay, the heat duty is slightly less than the corresponding heat of reaction because our entering stream was at 110 degrees C, right? But we're gonna keep the reactor temperature constant at 154.6, right? And so my reaction is going to be it's exothermic. It will be releasing heat, and so that will also be used to elevate the temperature up to that desired temperature. If I look at my product stream, right, essentially this predicts that a reaction is isothermal or irreversible and essentially goes to completion. Right, we're essentially consuming all of our DTBE. I'm not able to specify conversion. Right, and so the DTBE in our product stream is essentially 0. But that's a Gibbs reactor. So the beauty of the Gibbs reactor is I don't need to define the chemistry whatsoever. This was useful for project 1 where we had a stream that was natural gas and some pollutants, and we were trying to mimic a flare, right? And so we just sent that stream to a Gibbs reactor without knowing all of the combustion reactions that were of interest, to the problem. We could just send it to Gibbs reactor and let it handle what that corresponding distribution of products should be. Okay. But yeah, that's it. I could also run adiabatically. Okay, and so it'll use that temperature as an estimate of my temperature. Okay, so if I run adiabatically, there's the calculated temperature. Okay, the heat of reaction remains the same. Okay, and still essentially my reaction goes to completion where I have no DTBE left. Okay, but that's my Gibbs reactor. And sometimes this could be useful for early design processes in which I don't exactly know the chemistry, and I can still use this to try and model or determine what that product distribution would look like. All right, so with that, I'm going to stop. Next, we'll move on to PFR and CSTR, presumably next class, also with a batch reactor.